This is VLSI data conversion circuits, lecture 41. In the last class we saw a top level view of how one would make a practical flash A to D converter, and the key building block in the converter is the comparator array, right, which means that we have to learn how to make a comparator. So the basic idea behind a comparator, as we saw, was to detect whether an input is greater than a reference or not. So let us try and explore some approaches, circuit approaches that will potentially make this possible. To keep things simple, we first start with the simplest possible reference, namely 0. In other words, we would like to figure out if some analog voltage, say stored on a capacitor, is greater than 0 or less than 0, right, and we want to make what we are interested in only, we are not really interested in the absolute value of the voltage, right, we just want to figure out if it is greater than 0 or smaller than 0. So what do you think one could do? What is the simplest thing that you could? So yeah, so one of these, one thing that suggests itself based on our experience is to say I am going to go on putting amplifiers in cascade like this, alright, and as this delta V keeps going through this chain of amplifiers, right, here it will be A times delta V, A square times delta V, A cube times delta V, and so on. Eventually these amplifiers, which are running off of supply voltages, positive and negative, will eventually saturate, correct. So in this particular example, if there are 3 amplifiers, the output voltage, if delta V is sufficiently large, will reach a logical level, right, which is either VDD or VSS, alright, okay, because these amplifiers presumably cannot go on producing output voltages which exceed the supply voltage, okay. But clearly we see that there is definitely a range of inputs which will fail to produce either VDD or VSS, which are or voltages close to that which are recognized logic levels, okay. So what is the minimum voltage you can resolve? So if you assume that the logic levels you want are VDD and VSS, the resolvable input range consists of voltages which are beyond VDD minus VSS by AQ, right. So this is the smallest resolvable input, alright, and in order to increase the resolving capacity, what do you think one can do? You go on increasing, put more and more amplifiers in cascade, okay. So please note that the linear range of these amplifiers is hardly a concern. We are not interested in making these linear amplifiers at all, right. We are only interested in raw gain, and why we are only interested in raw gain, we are the characteristic we are trying to realize is very nonlinear, right. It is we are trying to realize an ideal signum function, right. So there is no point in trying to make each of these amplifiers linear, and of course as always we would be interested in trying to do this with as efficient a realization as possible from both a hardware and power point of view. Another way which is probably not very apparent at first sight, okay, is to say I have a capacitor with a voltage delta V, right. So, this earlier approach is the cascade of amplifiers approach. And please note that even though we have said this is A cube V, in practice every amplifier will have finite bandwidth. So, this A cube V will only appear after some time, right, which corresponds to the delay, so to speak, of this amplifier chain. Now, yet another way of trying to figure out whether this delta V is greater than 0 or less than 0 is to say the following: if this voltage is greater than 0, right, I will attempt to make it, I will attempt to increase it. If this voltage is less than 0, I will attempt to decrease it. So, as time keeps going along, right, if it was greater than 0, it will keep going up and up and up, hopefully eventually hitting the rail. And similarly, if delta V is smaller than 0, it will keep becoming more and more and more negative, eventually hitting the negative rail, right. So, this way, after a sufficient amount of time has elapsed, okay, the output is either VDD or VSS, okay. So, it is like in India where the rich keep getting richer and the poor keep getting poorer, right. So, how do you now push this node voltage up if delta V is greater than 0? What I mean, if you want to push a node voltage up, what should you do? You want to push current in, but that current must be dependent on delta V. So, if delta V is positive, you want to push current into the node. If delta V is negative, you want to push current out of the node. So, basically what you want to do therefore is to have a current source which is controlled by delta V. Let us call this clearly a voltage controlled current source. So, if delta V is positive, this current is Gm times delta V this way, and what should I do? I should go and feed it back like this, all right. You understand? So, what would be this voltage as a function of time if we started off with V of t initially? Let us call this C. C dV dt is nothing but Gm times V, with V of 0 being equal to delta V, all right. So, this is a first order differential equation, right, or if you think of this as a system, it is a single pole system, and where is the pole located? Gm by C, but where, I mean where in the Laplace plane is this? It is in the right half plane. So, this is actually an unstable system, correct. So, V of t therefore is delta V times e to the plus t by tau, where tau is nothing but C by G, all right. Okay, so what kind of clearly there is feedback here. What kind of feedback is this? Positive feedback, because if we break the loop and come back, right, the response at the other end of the loop is in the same direction as the excitation. So, this is positive feedback, or often called regenerative feedback. All right, and tau is called the regenerative time constant. Does it make sense? Okay. Now, what we will do is, apart from figuring out how to realize this with transistors, we will have to observe that again in practice this GM is going to be powered off of some supplies, correct. So, even though in principle the output voltage should go to infinity, in practice it will be limited either to the positive rail or the negative rail. So, from a hardware complexity point of view, this is a very simple structure where we use positive feedback to obtain gain, whereas the cascade of amplifiers would have required a whole bunch of amplifiers to do this. You understand? And linearity etc. are not really important. All that we need to do is figure out if the input is less than 0 or greater than 0. So, this is an ideal candidate for doing this. And if you want to have more gain, what does this mean? How will you get more gain? I mean, the gain of this contraption, if you can call it that, is basically e to the t by tau, all right. Okay, is the regenerative gain that you get in a period tau. So, one straightforward way of increasing the gain is to wait long enough, that is all, right. So, more t means more gain. Of course, most of the time you do not have the luxury of saying I am going to wait for 2 days for this to give me my decision, right. So, in practice what happens is that the amount of gain you have is limited to the amount of time you can wait for. In a flash converter, for instance, right, the comparator array has to make a decision within a finite amount of time. That time cannot exceed 1 clock cycle, because the array has to get ready for the next input, right. In the worst case therefore, or rather in the best case for the comparator array, all right, one can say okay, I am going to take the entire clock period to make a decision, right, and then in that that infinitesimally small time before the next input comes, I am going to do I am going to prepare myself for the next input, which is, as you can see, a stretch, right. But at least in principle there is, that there is a finite amount of time before which you need to make a decision. So, if that time is taken to be t, the minimum resolvable input is the time taken to reach a logic level, right, divided by the gain as usual. So, that is nothing but say VDD divided by the gain, which is e to the capital T by tau, where T is the time available for comparison. Does make sense? So, let us say this is the time available, capital T, and let us say this is VDD, right, and let us say the input started out here. Okay. Then what happens? The input regenerates and the output is plus T, I mean at time equal to capital T is without ambiguity the full level that we want, correct. Now, as the input keeps getting smaller and smaller, what happens? Okay, this happens, right. As you can see, the delay of the comparator therefore depends on how close the input is to the threshold, right, and if the input is very, very close to the threshold, the output may not regenerate to a logic level, okay, and in this case the comparator output is supposed to is called metastable, okay, where the input is too small to result in a valid logic level. Now, if the output is not a valid logic level, what do you think is the problem? I mean, clearly the output of the comparator array is being read by several levels of several stages of logic, right. When you say the output of the comparator is not a valid logic level, it means that in digital parlance it is that X, right, where what the following stage of logic interprets the signal as is anybody's guess, right. So, the same signal could be interpreted by different logic blocks as being either a high or a low. In general, this will lead to errors in the flash output code, okay. So, in other words, the delay or the time taken for a comparator to make a decision, right, is dependent on the magnitude of the input. A large input, in other words an input which is large when compared to the threshold or far away from the threshold, will result in a decision which is very quick, whereas an input which is close to the threshold, right, will take a long time to regenerate. Therefore, if you have only a finite time, it means that you will not get a valid logic decision in that finite amount of time if the input is very close to the threshold, okay. So, this is very similar to what happens when you go for an interview, for instance, right. What is the committee trying to do? It is trying to make a decision whether you are in or out, okay. So, if you get kicked out of the room in a minute, definitely for sure that it is one of two things, either you are in or you are out. Presumably the committee does not want to waste its time too much, right. So, if it is a sure shot candidate, then you are through, or if you are a sure reject also you are through, correct. The moment you are on the border is when they would like to spend a lot more time and try to figure out whether you are above threshold or below threshold, you understand. So, if you go into an interview and then you spend a lot of time in the with the guy who is interviewing you, then you should be worried, right. okay. All right. I mean, of course, we come out very quickly. I am sure you know yourself whether you know you're in or out. Okay. So, so that is what this metastability is all about. Okay. And this will, as I said, will cause errors in the output of the flash converter. All right. So, the way of increasing the gain of the comparator, or to reduce or make the minimum resolvable input smaller, what do you think you can do? I mean, of course, capital T is fixed. So, the only other variable you have is you make sure tau is small as possible. So, in other words, tau is C by Gm must be made as small as possible, which means, I mean, you know, the Gm finally you know is going to be implemented using MOS transistors, and these transistors themselves have inherent capacitance. So, there is no need to deliberately put another capacitance there, right. The input which you want to make a decision on can be stored on the parasitic capacitances of the MOS itself. Okay. All right. So, we make C as small as possible, and therefore, which means that you do not put any explicit C at all, you are depending on the parasitic capacitance of the MOSFET. So, basically you are limited by the FT of the MOS transistor, because Gm by C, where C is some function of all the parasitic capacitances in the MOSFET, is proportional to the FT of the device. So, if you know, if the technology improves by scaling down the length, for instance, then to get the same Gm you need a much smaller capacitance, right. Gm for a transistor is mu n Cox W by L times Vgs minus Vt, whereas Cgs for instance is Cox times W times L, correct, which means Gm by Cgs is mu n Cox into Vgs minus Vt by L square, sorry, mu n into Vgs minus Vt by L square, right. Clearly, as mobility of the carriers increases, you expect to have a faster transistor. Okay. If Vgs minus Vt increases, you have a larger electric field pushing the carriers from the source to the drain, and if L if L decreases, the Ft goes up as L square. And why does that make physical sense? But why L square?
Because it reduces the capacitance and increases the same.
Well, yeah, I mean, in more physical terms, if you reduce L, two things happening. The field strength is increased, because it's the field which is propelling the carriers is Vgs minus Vt by L, right, and the carriers have to travel a shorter distance, right. So, it goes as L square. So, as you keep increasing the oomph in the technology, right, the comparators, I mean the regeneration time constant becomes smaller, which means that the minimum resolvable input for a given capital T, that given time you have for the decision becomes better, right. But unfortunately, as technology keeps shrinking, you are also expected to make converters or circuits which are faster, so that I mean you will find that the design in a shorter channel MOS technology is just as challenging as one in a longer channel technology. Okay. Now let us try and look at some circuits which allow us to do this. In practice, therefore, what one must do is to try and realize a transconductor in principle, and it turns out that most circuits these days on a chip are what are called fully differential circuits, okay, as you might have seen in your analog IC design class. So, information is not carried on one wire, but on two wires, and the information is not the absolute potential on either of the wires, it is the difference between these two potentials. For example, let us say you have two wires carrying voltages V1 and V2, okay. The two wires voltages can be represented as V1 plus V2 by 2 plus V1 minus V2 by 2 and V1 plus V2 by 2 minus V1 minus V2 by 2. This is the so called common mode voltage, and this is the differential mode voltage. So, this is VCM plus VDM, and this is VCM minus VDM. Any two voltages can be expressed in this fashion, right. So, the advantage of having information being carried on two wires rather than one is that in a noisy environment, if both these wires go through the same environment, then all noise sources will add to both these wires in the same way, correct. Therefore, only the common mode voltage of these two wires will be affected. However, the difference between these two potentials is still maintained in spite of adding noise to both these wires. That is the motivation behind going fully differential, and all state of the art signal chains are all or almost always fully differential, simply because ICs are expected to operate or analog sub blocks are expected to operate on the same chip with a lot of digital stuff, and the digital circuits are switching at a lot of gates switching at the clock speed. So, the supply and ground can be extremely noisy, okay. Now, if you have a fully differential analog system, then supply noise or any other noise source for that matter, which is common to both the paths, right, can be rejected, because every time you are only measuring or you are only working off of the difference between the two wires, right. So, now earlier I mean we were trying to resolve whether a single voltage was greater than 0 or less than 0. Now, if we take this or make this fully differential, what are we trying to do? So, this is a single ended comparator, okay, as simple as it can get. Of course, this needs to be a lot more embellishments before this can be made a practical circuit, but at least the basic idea is this. Now, if you are now dealing with an input which is differential, in other words the two wires are VCM plus VD and VCM minus VD, what are we trying to accomplish? What we are trying to do is trying to figure out if VD is greater than 0 or VD is less than 0. Does it make sense? Correct? In other words, we are trying to figure out whether VCM plus VD is larger or VCM minus VD is larger. And please recall that VD can be either positive or negative. So, going by our discussion on the single ended version, what do you think we would do for a differential version? Pardon? No, what is the analogous schematic? So now you have two capacitors in principle, one holding VCM plus VD and the other holding VCM minus VD, and what do we need to do? We need to sense what were we doing earlier in the single ended case. If VD was greater than 0, we were pushing it higher by using a voltage controlled current source which only depended on VD. Now what should you do? We look at the difference between these two nodes, correct, and then pump currents such that if VD is positive, so let us say this must be GM times VD, all right, and similarly if on the other side you must pull current out of the other node. Does it make sense? Earlier we were looking at one voltage and pushing one current. Now we are looking at the difference between two voltages and pumping a current which is the difference between, which is proportional to the difference between these two voltages. Does it make sense? Okay. So please recall therefore that this is plus VD and current is being pulled out of this node this way. Similarly, this voltage is minus VD and current is being pushed out. So can you think of a simple circuit solution that will do this? If this voltage goes up, current is being pulled in. Yeah, it is a transconductor, all right, but what is this, the simplest circuit that you can think of which will enable you to do this? A CMOS inverter, that is right. So let us say this is VCM plus VD and this is VCM minus VD, alright. If VCM was chosen to be the natural trip point of this inverter, okay, what is the meaning of natural trip point of this inverter? What are the characteristics? How does the CMOS inverter behave? Vi and Vo, and this is, you know, that magic voltage Vx where there is high gain, right. So, if you bias it precisely at Vx, what is the what is the speciality of this Vx? Slope is very high, but what can you say about the current through the NMOS and the PMOS transistor? It is the same, correct. So, if this VCM is chosen to be the trip point of this inverter, right, then if Vd is 0, this current is, in other words, for the inverter, if we chose this to be the VCM, right, then if Vd was 0, what would this current be? It would be 0 by definition, correct. Now, if Vd was positive, what will happen? How much current will flow here? Gm times Vd. Does it make sense? Okay. Now, what else should I do? Is that the whole story? I need to do something else. Yes? I need another inverter which senses the other node. All right. And therefore, if Vd is higher, or rather if Vd is greater than 0, what will happen is that this potential will eventually go to, this will keep going higher and higher if Vd is greater than 0, which means minus this node VCM minus Vd will keep going lower and lower, correct, and vice versa. Eventually, the output will become so high that the inverter will saturate, giving you a valid logic level. Does it make sense? Okay. So, now let us get down to drawing circuits. It is two inverters connected back to back. Okay, and we know that we would not want to deliberately increase the parasitic capacitance at the input nodes for fear of increasing the regenerative time constant. In any case, there are so many devices, so there is bound to be a lot of parasitic capacitance. So, you can simply use that parasitic capacitance to hold the analog inputs. that clear? Okay. So, once this circuit has taken an input and made a decision, right, you must now get this guy ready for the next input, all right. You understand? So, there must be a way of, we need two things. One, once we made sure that the correct input is written onto both these nodes, right, further variations in the input must not go and disturb the decision making process, right. I mean, just like if you have an interview, I mean, the candidate goes in and that is it, right. It is not like, you know, the other candidates also walking in when this candidate is being interviewed, isn't it? Okay. So, you must have a mechanism by which you let in somebody and hold him in there, right. So, you must need two switches which will disable the connections to the input of the latch all right. So, let us call this phi 1. So, the sampling instant of the latch, this by the way is called a latch, as you all know. The sampling instant of the latch is nothing but the, what instant is the input being sampled onto the two nodes of the latch? Yeah, it depends on phi 1, and which edge of phi 1 is the sampling instant of the latch? These switches are on when phi 1 is high and off when phi 1 is low, right. So, at what edge of phi 1 is the input? What are we interested in? We are interested in the voltage held on those two nodes, okay, to make a decision. So, what are those two voltages? No, is the question clear or it is not clear? No, the input, let us say, is doing this, correct, and this is phi 1, right. What is the voltage which is finally held on that parasitic capacitance in the latch? In the, on the falling edge of phi 1 is when the input is being sampled onto the latch, okay. So, that is something to bear in mind. The falling edge of phi 1, okay. All right. So, let me ask you another thing. When the input is being sampled onto these two parasitic capacitances, should the two transconductors be active or not? Let us see, okay. So, the input is being sampled onto these two nodes. Do you think it makes sense for these two guys to be active during that time? Yes, no? Why no?
It can force the. If I force it, it can consume a current out of it, out of the input.
more fundamental reason why you do not want it? Is the question clear, right? What we want to do is the following, we want to have VCM plus VD and VCM minus VD on these nodes. So, to that end what we do is we will attempt to write using two switches which are clocked with phi 1. So, this is VCM plus VD which is time varying, and this is VCM minus VD which is also time varying. Does it make sense? Okay. So, during the time phi 1 is high, do you think it makes sense for these two people to be making a decision, I mean to help in the decision process? Yes, no?
This will be trying to write some value, but that inverter output will be pulling up.
Correct. So, basically these guys will be pushing currents into these two nodes which are dependent on VD of t, which is not yet settled to the right value that you want to make a decision on, correct. So, it does not make sense for these two guys to be active during the writing process, alright, which means that during the writing process, that is when phi 1 is high, these two inverters must be, what must be they be doing? They must be disabled. So, what do you think I can do to disable them?
Routing by cutting off the supply.
So, one straightforward way of doing this is to have switches in the between the supply and these inputs, these inverters as well as ground and the inverters ground, so that when phi 1 is high, phi 2 is low, right, and as usual phi 1 and phi 2 are non overlapping clocks, alright. So, when phi 1 is high, the input is being written into the latch. When phi 1 goes low, I wait for a certain time and then get phi 2 to go high, and what happens then? At the falling edge of phi 1, the two parasitic capacitances have on them stored the two inputs on which I want to make a decision. When phi 2 is enabled, or when phi 2 goes high, these two switches are enabled, causing the inverters to spring into action, and the voltage which is larger becomes larger, the voltage becomes smaller, and these two nodes which were at VCM minus VD and VCM plus VD, depending on the sign of VD, will either go to VDD or to ground. Okay, in this case we have chosen the negative rail to be ground. Okay. Now, once a decision has been made, right, somebody else needs to store that decision, correct. So, you can always have a flip flop, for instance, or another stage of memory which will hold what decision this latch is made, and then the latch must get ready for the next input. But couple of things one must observe. After a decision has been made, what are the voltages at these two nodes? One will be VDD, the other will be ground. Which one will be VDD and which one will be ground depends on the input difference VD, right. But the key point is, if this latch has to be made ready for the next input, these two initial voltages are VDD and ground. So, if I connect them directly to the input, what danger do I run?
Or something, then there can be a charge redistribution.
No, whoever is driving this VCM plus VD node, he has to discharge or charge the
Correct.
capacitor.
So, these two parasitic capacitances are charged, right, these two, let us assume that both of these are nominally identical, and one of them is initially charged to VDD, the other one is charged to ground, correct. The inverters have been disabled, why? Because we are trying to write the next input. So, what we have is this scenario where we are attempting to write VCM plus VD and VCM minus VD. In principle, if these voltage sources are ideal voltage sources, there is no issue, because these ideal voltage sources, the time taken to charge this capacitor is 0. In practice, the voltage source that is trying to write into these nodes will have some finite output impedance, correct. So, let us call that output impedance RO, all right. So, what do you think will happen to this voltage, for instance? Pardon? No.
minus
The two things happening, okay. VCM plus VD is attempting to get onto Cp with a time constant R0 Cp. At the same time, VDD is trying to get discharged again with the time constant R0 times Cp, correct. So, if this R0 times Cp is large, then what will happen? The final voltage across Cp will be some VCM plus VD into 1 minus e to the minus whatever T by tau, T by R0 C, not to get confused with the earlier time constant, right, plus VDD times e to the minus tau by R0 Cp. So, at the end of a time t, the voltage which will be on Cp is not truly the input voltage, but it also remembers the past, okay. This will be particularly problematic when the previous input caused the output voltage, this particular node, to go to VDD, and the next input will potentially cause this node to go to ground. You understand? So, in other words, this is terrible when VD is positive in one cycle and just negative in the next. Correct? Because if VD was positive in the first in one cycle, the output has regenerated to VDD, and in that extra time we need to, we need, for the next input we need to discharge this to, we need to get rid of this VDD, but that takes time. So, at the end of the time t, a part of the previous decision has still remained on the parasitic capacitance, right, and this is clearly going to corrupt the next input, which is only, let us say it is mildly negative, then this error will add to small negative value, potentially making it positive and cause the comparator or cause the latch to give you an incorrect decision, right. So, this is what is called hysteresis. All right, where the latch remembers the past. Okay. So, the next class we will figure out what to do about this.